Hello, this video is entitled Measures of Variability. Now we've studied measures of central tendency like mean, median, and mode. And now we're going to look at numerical values that indicate how much the data is scattered. You know, how far are the numbers close together? Are they spread apart? Like that. So the first one, and by far the easiest thing you'll ever see for variability, is range. And range right here is strictly the maximum data entry minus the minimum data entry. Just a fancy way of saying the largest value in your set minus the smallest value in your set. So we look through here, and then unsorted, so you're looking for the largest value. You know, if the data was sorted from lowest to highest, then the largest number would be on the right and the smallest would be on the left. But that is not true here. So 24 is the largest number, 2 is the smallest, 24 minus 2 equals 22. All right, so I think that's enough of range. Not too complicated. And now we have something called deviation of a data value that's going to lead to a couple other important terms here. Now, whether it's sample or population, it's calculated the same way. You take whatever particular data value, X, for example, in this data set up here, X just represents each individual number like X1, X2, X3. So for any particular value, you would take that X and you would subtract the mean. So sometimes the deviation will be positive, sometimes it'll be negative. And here's a data set with 12, 13, 7, 5, and 9. And I notice I'm labeling it a sample. That doesn't affect the mean, but it is going to affect something we're about to learn here shortly. So you just add them up. 5 numbers up, I get 46. Divide that by 5, we get 9.2. Now to find the deviation, here's an example before I show you what this is down here. But this is the deviation. You would take, 12 minus 9.2, 13 minus 9.2. You could do a deviation value for each number in your list. So let's suppose that we wanted to take, let's say, what if we wanted to average the deviation? So we're trying to get some sort of new measurement of variability here where we take the average of the deviations. Well, that sounds good in theory, but there's a problem with that. The sum of the deviations always adds up to 0. Now, I could prove that with formula, but I don't think that's necessary, but I could. It would always add up to 0, not a fluke. So if in this case, if you took 0 divided by 5, you get 0. So that really doesn't tell you much. I mean, there's only one way that a data set could have 0 deviation is if all the numbers were the same. So even an average deviation of 0 doesn't tell us much. Because doing it this way, it would be 0 every time. Every data set would have an average deviation of 0. No good. All right, to sort of resolve this issue is we took out the idea of negative deviations, meaning we don't care. So, for example, let's say in this particular set here, 7 minus 9.2 would be negative 2.2. We don't really care about it being negative as much as we care about it being 2.2 away from the mean. So it's kind of like positive or negative, same thing. Now, one way, could have possibly have taken care of that might have been to use absolute value, but that's not actually practical because that's not how it's done. Here's the other way you get rid of that negative, by squaring the deviations. So that way, if a deviation number is positive or negative, or it could be 0, but that's not affected, 0 squared 0, you square it and you'll get a positive number. So that takes care of the issue now of these all adding up to 0. Which, as I said before, now the only way that would add up to 0 when you square them is if every number's the same. Now there's no chance it'll add up to 0 now otherwise. So this one you see is taking the, now we have this thing called the sample variance. It's labeled as S squared. Sample variance. Now, that is calculated as taking each deviation from x1, x2, all the way to xn, meaning your last number, subtracting the mean, and squaring each of those values. guaranteeing they'll be positive. Then you divide by n minus 1. We'll talk a little bit more about the n minus 1 coming up in a little bit. Let's see. And this term, in the numerator, remember that's your summation signal, symbol. Anytime you see that, it means adding stuff up. So it's adding all these up. So this also is called the sum of squares. I don't think we'll be tested on that or anything, but just thought I'd mention it. Sum of squares. So essentially, you're taking the sum of squares and dividing by n minus 1. Well, let's take a look at this. So you take each number here, you subtract 9.2, square it. The next one minus 9.2, square, so forth, so on. You get a total of 44.8. Now that's not your sample variance, that's just the numerator part of the sample variance up here. You divide by n minus 1. 44.8. And then divide, n is 5 because there's 5 numbers. So 5 minus 1, of course, is 4. And you get 11.2. So I didn't finish that in the calculator here, but 44.8 divided by 4. But so you see, I just did each of the deviations and just squared them and did it in one continuous string, like I wrote it out right there. Yeah, I didn't need to see what each one of these were individually. I mean, you could if you wanted to, but let's add them all up at once. So the sample variance is the sum of the squares divided by n minus 1. And here it is again. There's the formula again. Now we have something called sample standard deviation. We're going to be using standard deviation quite a bit in this class, more so than variance. But they relate to each other, so that's the reason. Is the sample standard deviation is the square root of the sample variance. In fact, that's a rule that's always true. Standard deviation is the square root of the variance. Later on, we're going to have a variance formula that's defined as n times p times q, which you'll learn what that is later, of course. That's the variance. That automatically means the standard deviation will be the square root of npq. So standard deviation is always the square root of the variance. Now, the standard deviation is more commonly used because, you know, when you've kind of squared those deviations, you've kind of altered their values quite a bit. So the square root sort of brings it back down to a more relevant number that can work better with the mean in determining information about data sets. But you see they relate to each other, so once you calculate the variance, you didn't waste a lot of time because you still need to get the standard deviation, square root to get the standard deviation. I just arbitrarily chose 3 decimal places here. So S is sample standard deviation. It would be the square root of this 11.2 that we found right here. Right there. And it's 3.347. Now this is called a shortcut formula, and you can use this one instead of doing all the deviations. It's up to you. Of course, you can also use, if you're just using a basic calculator, but if you've got like a TI-84 or something that can do this, I'm going to show you how to do that here in a minute too, and you don't have to use any of these formulas. Well, I'm taking these same 5 numbers. I mean, what's nice about this formula is, so it's calculating the sum of squares. And what I like about it is you don't have to use the minus over and over and over repeatedly, but you might find the sum of squares formula easier to work with. This one I'm showing you right now would be, I think, better if you had a lot of numbers. It would really be beneficial. Now this red is just representing the sum of squares. So what you do is we need 2 columns here. Put all the x's, I just wrote them, they're the same data set. Now you can do this vertically or horizontally, that makes no difference. Put all the x's there, then I square each x. So 12 squared is 144, 13 squared is 169, so forth, so on. And I'm going to need the sum of both of those columns. Now once this formula is a little weird, you got to kind of get used to it there because this looks a lot alike, but these 2 things, but they're not. The first one, because of where the parentheses are, it's the sum of the x squareds. And meaning it's this number right here. It's the sum of the x squared column or row. Minus the sum of the x's, which is that 46. You square that number, then you only divide that number by n. So notice how I have this written. Only the 46 squared is divided by 5. If I wanted all of that divided by 5, I would have either written it as a larger fraction, put everything all over 5, or I would have used parentheses, which is, in a calculator, anytime, you want an entire thing with addition and subtraction to divide by another one, you must use parentheses. But here it's okay because I don't want that. So see, the calculator, and without putting parentheses, will interpret this correctly. If I go 468 minus 46 squared over 5, it knows only the 46 squared over 5 is by itself, because the order of operations is going to do the exponent and the division first before the subtraction. Well, anyway, this result gives you 44.8. Now, sometimes people will jump the gun and think that's the answer to the sample variance. No, it's not. You still have to divide by the 4, which was the n minus 1. It's just giving you a different way to get that same 44.8 that we got right back up there. It's just a different way to get that number. And then you still divide by 5 minus 1, and you still get the 11.2. So if you are using, just a regular kind of scientific calculator, you can choose either way to do this. Now, if you're using the TI, this is a little older version of the calculator. Well, I should have warmed mine up here, but anyway, I can put these in there. But I'll just explain real quick. You go Stat, Edit, and it's going to bring up this menu right here. If your calculator, I just helped somebody with this in class recently. If sometimes it'll start out with an L4 or something messed up here. What always works for me is I just do a memory reset. Somewhere in the calculator you can do a memory. I guess I could show you that real quick, couldn't I? Only way that would be affected is if you had any programs in there. If I go second, memory right down there above the plus, 7, reset, all RAM, reset. And that works every time. That gets all the bugs out of there, so if something was going wrong, that would fix it. So I've helped a lot of people over the years to do that. So I don't know what causes it either, but sometimes they'll start out, they'll say L4, L5, L6, and anyway, it's just easier if it starts out with L1. So 12, 13, 7, 5, 9. So I'll go Stat. I like the way that these light up on the screen here is red. Stat, Edit's the first one, enter. So I'm going to go 12, 13, 7, 5, 9, and then I'm going to go second, quit, stat, calc, second, quit, and go to stat, calc, 1 var stats, and as long as you have it in L1 here, you're good. Now, I did some stuff in the section on the means where you can actually use L1 and L2 when you have 2 sets of numbers there. Well, somebody was having problems with this variance. Anyway, you don't want that. If there's an L2 sitting right there where that's blinking, delete that out of there. All right, calculate. And there's the standard deviation, 3.34, sample standard deviation, because the one below it's going to be something else here in a minute. 3.3467. Now, the calculator does not give variance, only standard deviation. No problem. So if you go from variance to standard deviation, you take the square root. That means you would do the opposite the other way. So to go from standard deviation to variance, you square the number. So I didn't type in all of it. Well, here I did. I typed in all of it, but I don't know if you have to or not. But anyway, whatever the case may be, you type in the number. If you want to type it all in there, hit the square key, and then there's our 11.2 right there for the variance. And there I have it in writing right there, what I just said. Here's another data set. And I wrote them horizontally this time. Now, I didn't even do this one by subtracting all the deviations. I did it by my shortcut formula. You can try it. If you're going to use it that original way I did it, it would be good practice for you if you want to try to do it. So one thing I like about this too is that first problem, what was the mean, was like 9.2. It kind of comes out nice and clean. But if it had more decimal places in it, you'd want to keep a few of them for accuracy purposes, but it'd be a lot more tedious to have to type in 4 decimals over and over and over or something like that. This formula doesn't even to use the shortcut formula right here. Even though the means in the original formula, you don't need to use the mean in this formula at all. So you don't even have to calculate the mean. Another reason I like it. Not that the mean's that difficult, but it just saves a step. So here I got the x's. There's the sum of the x's is 54. The sum of the x squared is 540. So I take the sum of the x squared, which is 540, minus 54 squared, the sum of the x's. Just the 54 squared is divided by 7. And then I went ahead and just used 4 decimals here. I just, just to help with accuracy. I got 123.4286. So the sample variance then will be the 123.4286. There's 7 numbers in here, so you subtract by 6. You get 20.5714 is the sample variance, and therefore the sample standard deviation would be the square root of that number. It makes it 4.54 roughly. I'm not sure if I did this one in the calculator. Oh, I didn't show, okay, there's that number, but I didn't show the entering of the data. But if you want to try it, try it yourself, process the same, enter the numbers in, stat, edit, list, put the numbers in, go second, quit. And then, anyway, long story short, what did we get for the S there? 4.54. And then there's the calculator screen, 4.5355, whatever. So, okay, we got it right. Now in Excel, of course, you can't use Excel for any in-class exams, but anything that's not in-class homework or whatever the case may be, you can do it this way if you want to. Now you have to go to check and see if Excel data, that data analysis needs to be there. If that's not there, you have to do a add-in. I think you go File, Options, Add-in, Add-ins right there, and go through the process. You could always watch. I think there's a nice. Well, I'm sure there are plenty, but brief YouTube videos that would show you how to do it. That's how I learned stuff I don't know how to do. And so, yeah, you have to. It's like an add-in, and once it's there, it's there. You don't have to add it in every time you use it. But actually, I'll show you real quick how to use it, since so you can see me do this live here, I guess. So I guess I could do it for those same numbers. 3, 11, 15. And 2986. All right, so once we have that, I go to data analysis. I choose descriptive statistics, which is still there probably because I just used it. Descriptive statistics. I need to indicate what values they are. Yeah, it gave me trouble with this earlier. Oh, okay, there we go. Now I can select them. Yeah, or I could have just typed them in there. Now, okay, now I got it. And then output range. I just always start this off as just in this case where the cell is highlighted at M1. I'll just go M1. You don't have to put a finishing point there because we'll just let it go to the right. It'll go to the right and down. You know, that way it'll just kind of take care of itself. And then the summary statistics box needs to be checked. Then we click OK. And then that should match what I have. I'll go back to that, but there's the Excel only shows sample. We'll talk about population in a minute, but there's the sample standard deviation, and there's the sample variance, which I got doing using the formula, the 20.5714. And we'll go back over here and see those. So yeah, and I highlighted those right here. Alrighty. Population variance. So now we're talking about a data set that's a population. Now, any question you'll be asked, you know, well, the problem should be clear whether it's sample or population, because this is important. It's not that important for a mean, because we learned in the last section that the calculation for the population mean and the sample mean are identical. But this is slightly different. Now, not just because of the notation, but there's one slight difference here. Now, the first thing I'm going to show you is notation. That little crazy looking O with the little tail at the end of it here, like that, that's another Greek letter. They like using Greek letters for population parameters. Remember, we had that one. There it is right here, the mu. That little funny looking U thing, the mu. And this is called sigma, lowercase sigma. Actually, the little zigzag there is upper sigma, and this is lower sigma, but that's all right. I mean, you don't have to memorize this for test purposes, but I'm often going to be saying, you know, I'll say like sigma squared or something like that, so it's good to know what that means, just so you can follow along with what I'm doing. So other than the slight notation, so instead of changes, which we have, you know, it's sigma squared instead of s squared, and we have mu here instead of x bar, but they're still the means. And now the population size is denoted by capital N instead of lower n. But it still just means how many numbers do you have. That's all it really means. Now notice, here's the difference. Is we divide by n instead of n minus 1. You can use that same shortcut formula to get that sum of squares in the numerator, but you would divide your answer by n instead of n minus 1. And now, okay, now we have the population standard deviation, which is just sigma without the square. That's how you know it's the variance. If it's got the square on the exponent. That's the easiest way to tell it's a variance right there. If it doesn't have the square, it'll be standard deviation. So once again, as I mentioned earlier, if it's a standard deviation, it would always be calculated as the square root of whatever the variance was. So here I'm writing it with that shortcut formula, and then we're just dividing by n instead of n minus 1. So let's see if I did, I guess, okay, I thought I had the other. No, I didn't, but I'll just mention this. So let's say, go back over, I'll just scroll back up to this one, that first one. Right there, yeah. So let's say you were told in the problem that this data set was a population instead of a sample. You would take that 44.8 and you would divide it by 5 instead of 4. So the numerator is not affected at all. It's the denominator that's different, and then of course that will make the answer different. So let's come down here. So here I just took a new data set, but you see it's telling you it's a population. Find the variance and standard deviation for the population. Therefore, population, standard deviation, and variance. Of course, I'll show you this in the calculator too. I don't know why I didn't. Oh, okay, I didn't input the data, but I also have it in the calculator. I was worried that it wasn't there, but I would have just shown it. 210,659. So here they are in this column, and then I squared each of those numbers to get this column. The sum on the left is 32, sum on the right is 246. And then so you would take 246 minus 32 squared over 5, because there's 5 numbers. Remember, that number 5 right there would be the same whether it's sample or population. That makes no difference. It's this bottom number that's the difference. If this would have been a sample, that would have been 4. Population, it's 5. So I get 8.24. And then the population standard deviation would then be the square root of that number. So roughly 2.87. Now before I look at this, I'm going to skip this for a second and jump down to the calculator. And the calculator gives you both standard deviations. We saw S a few minutes ago. Right below S, there's your little sigma. That's your population. 2.8705, whatever the case may be. So had this been a sample standard deviation, it would have been 3.209. And just like I did in the example, so let's say you're using a calculator like this, which is fine. Use a calculator. And the question is asking for population variance. You would have to then take this number here and square it, not square root it. So once again, variance to standard deviation is square root. Standard deviation to variance is square. So you take 2.8 some blah 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 and you square it and you'll get that 8.24 right there. I don't know if you'll ever need this. Is just if you were doing this in Excel and you didn't have the fancy calculator. I've never had to use this. It's just a little trick I came up with, a conversion from one to the other, meaning if you had an Excel output and you needed population, because Excel, there's actually a population variance command and a population standard deviation command within Excel. I think it's pop var or pop.var. You know, so you could use that. You can calculate it within Excel as an individual command. You know, you can just look it up and figure out what it is. But let's just say you had this output and you wanted to convert it just from the output. So to get the population variance, you take this sample variance number 10.3 and you would multiply it. There's 5 numbers, so it would be 5 minus 1 makes it 4 over 5, which is what I did right here, and that's the 8.24 that we got earlier. So that is that does match. And then the square root of it here is how you would convert the standard deviations. So 10.3 right there, that's the sample variance. But then we see what we've already calculated. See, there was the population variance. So that formula worked. So 10.3 times 4 divided by 5 is 8.24. So, all right, just a little trick. You never know if you might need that or not. Probably not. And I want to mention here that standard deviation is more commonly used than variance, since it works better to the mean with the mean. And I was mentioning numerically with the deviations earlier, but mainly with units of measure. So kind of when you square the value, you're squaring the units of measure. In this case, you know, like if it was dollars, you know, dollars squared would not be a very meaningful unit. But as soon as you square root it back, it's then back to dollars. Now here's something I just want to show you, because it might seem kind of odd, you know, why are we dividing by n minus 1 to get sample instead of n? There's kind of several ways to explain it. This is kind of a non-mathematical way, sort of, to explain it. Is you are dividing by n minus 1 to get a little bit larger result, you know, when you divide by a smaller denominator. So you essentially, to be on the safe side, you're kind of overestimating it to be safe. So it's a way to kind of, because a lot of times in statistics, you're trying to, use the sample variance, the sample standard deviation to approximate what the population would be when you don't have the population data. So once again, this is not on a test or anything. It's also known as what's called an unbiased estimator. It gets kind of mathematical here. In fact, I brought this up just to kind of scare you here if you really want to. This obviously takes a little more advanced mathematics than just regular statistics, but so they're trying to show that dividing by n-1 will make it an unbiased estimator, s squared of sigma squared. Okay, they're showing this bias part. Then now skip that, come down here to the little beauty. So with n-1, so isn't this delightful? That looks like fun, doesn't it? So we go yada 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 here. Okay, obviously we're not going to go through all that. Comes down here. Still going. Still going. Still going. The E stands for expectation, by the way, so we'll actually see that E come up in another context later. Long story short, we get to the end, and it equals sigma squared. So the expectation of S squared is sigma squared, meaning that S squared, with dividing by n-1, is considered an unbiased estimator of the population variance. So the n-1 needs to be there to eliminate any bias in your estimating. So that looks like a lot of fun there, doesn't it? Okay, all right, so the last thing I want to show you in this video is I often get this, asked in class. The numerical value for like a standard deviation or variance really doesn't make much sense often by itself. If somebody says, oh, the standard deviation is 4, is that large, not large? It's kind of, whereas the mean, if somebody tells you, oh, the mean of this data set is 62.4, or something, that might make a lot of sense in relation to whatever the data was. You might understand that clearly. But standard deviation and variance don't often make that much sense. So what I did here, just kind of put these in Excel just to show you. I took a data set of an example we did earlier, 12, 13, 7, 5, 9. I made up a new data set. Now I wanted these to have the same means because as I mentioned in here, we will see how to kind of compare them. Right now I want to compare them apples and apples here, both being the same mean. Because if you make the numbers completely different, you can't really compare the standard deviations. There is a way to do that we will learn later, but for now, this needs to be the case. So I made up 8, 9, 9, 10, and look at the mean, 9.2, 9.2. These data sets have 5 numbers with the exact same average. Now, notice that this data set on the right, the numbers are closer together, aren't they? They're not spread out as much, anywhere here. They went anywhere from 13 to 5, so they're scattered. So even though the number doesn't make much sense by itself, one thing that we can say is true is the standard deviation is going to be larger for the first data set because the numbers are more scattered. So like I said, and that proved to be the case. They had the same mean, but this standard deviation is 3.3466. I was assuming it's a sample here. And then the standard deviation is 0.8366, whatever the case may be. So that's all. You can kind of compare it that way, but by itself it doesn't make much sense, which is fine. But as soon as we start combining it with the mean here pretty soon, not in this section, in future section, then we'll be able to kind of pair the mean and to get standard deviation together to tell us information about a data set. Well, that concludes this video on measures of variability.